Isn't everything amazing valuation?
Conventional. All right. Hello. Welcome to Chalk Talk number whatever 375. The last Chalk Talk of the year.
That's all I gotta say.
What?
No. This is from 15 minutes ago, like some WBSD discussion episodes.
It's just intense.
What intense WPSD.
It was.
Aren't they always?
I mean, yeah, probably.
Is there an eraser? Oh, there is.
Well, we get. I mean, anything with Darren involved is very intense.
Yes. You are correct. All right, so today we're going to have, like I said in the announcements, last time we stopped and we're going to go over again to refresh each other and to refresh myself exactly where we stopped, because it was, we were kind of in the middle of things. And then we're going to take a little bit of a break and look at a couple of ways of solving nonlinear least squares problems, which sounds really scary, and it is. But then, like I said, this methods for nonlinear least squares problem by Haj and Madsen, it's actually pretty lovely to read, as long as you're not freaked out by the equations. And so what we're going to do is very carefully go through some of the equations, make sure that you're not freaked out, or mostly I'm not freaked out. And then hopefully you're not freaked out too, but that'll be okay. All right, so remember what we have. We've got, let's start out here. We've got an arbitrary mesh. Here we got our guy. There we go. And we want to bend him in a nice, controllable way. And think about this as a cool kind of way of doing embedded cage deformation. So what we're going to do is build a cage around this guy, typically by decimating him into nicely spaced vertices. And so, sure, sure, absolutely. Oh, right, the camera. Yeah, sorry about that. I switched the camera. Thank you very much. I totally forgot to do that. Now we're good. Now lights on. Our spotlights are slowly getting destroyed. All right. So we're going to decimate this mesh, boop, boop, and just put like little dots on our little character here. And then we went over how you hook these guys up. It's kind of a nearest neighbors thing, where you're going to build edges between a certain number of nearest neighbors. And the paper is a little deceptive in that it draws the connection, but it never draws something like that where an edge crosses an edge, because this mesh that this guy is embedded in is not actually a mesh, it's a graph. And it's basically saying that these guys are near enough so that they should influence each other. Then, at each one of these nodes, we're going to expand out here, we are going to store a rotation, and I think they're noting it with J's, aren't they? Yeah. Rotation sub J and a translation sub J. And so that's a 3x3 matrix that specifies a rotation, and that's a translation. And the whole thing is that once you have this, and they have a way, which we talked about last time, we're not going to even go over, is if we could deform this cage that surrounds our character in a neat way, then we can apply those deformations to the interior, the embedded character inside, or the mesh inside this cage, in a nice way. And so at each one of these nodes, when we deform this, we want to figure out the rotation and the translation on each one of these nodes that make it look nice, that makes it behave. And so last time we went over there and said, okay, well, what exactly is making it look nice? And they said, first of all, and we're going to write this down in a very specific way. I'm going to try to be neat about this. Number one, rotation. So we talked about this last time. There is an energy based on the rotation matrix at each one of these guys. Because we're going to start changing things. There's 9 variables here. This is a 3x3 matrix. So there's 3x3, and this turns into 9 variables that we get to mess with. And this is a 3-element vector. So that is another 3 things. So 9 and 3 things that we're going to be changing on this thing. And as you'll see in a bit, we are going to individually look at each one of these little entries in this matrix and make adjustments to them. So as we do that, as we make adjustments to those individual things, we also want to make sure that this matrix stays a rotation matrix. So they developed a little rotate operator on the rotation part. There's no subscript here. We're just going to do an arbitrary 3x3 matrix. And that's equal to the C1 dot C2 squared plus C1 dot C3 squared plus C2 dot C3 squared plus C1 dot C1 minus 1 squared plus C2 dot C2 minus 1 squared plus C3 dot C3 minus 1 squared. Okay. And we walked over this last time. C1 is this column. C2 is this column. And C3 is this column. And just really quickly, for people who weren't here, this basically says, if you dot one column with another one, they should be perpendicular to each other. They should have a right angle. And when you dot a right angle vector, or 2 vectors that are perpendicular to each other, or orthogonal to each other, you should get a 0. So we're going to take this, figure out what that is, and then square it. Pay attention to that square to make sure that negative values don't throw us off. We're just going to square it to get rid of the negative value. And we're going to do every combination. We're going to dot C1 with C2, C1 with C3, and C2 with C3 to make sure that each and every one of these vectors here are perpendicular to each other. Then we also want to make sure that these guys are unit vectors. So we're going to dot them with themselves. And this basically squares the length. And then subtract 1 from that and make sure that that is as close to 0 as possible. So this result should produce 1. 1 minus 1 gives you 0, square or some number, and squaring it, make sure it's positive. And so you want to make this as 0 as possible. And so we do that for each one of the columns. So far, so good. So then they said, okay, let's do this over the entire mesh, and try to write it here. E rot equals the sum of j equals 1 to m of the rotation of each one of these matrices. That's easy. So there's an energy term that looks like that. All right, fair enough. Step 2. We want to make sure, and they call this regularization. And at the end of last time, Joe Manchevitz pointed out a problem, and we're going to look at it and see if that is actually a problem, which it is. Regularization. And this is basically saying, I want, if I deform a node in this graph that's changing my character, I want to make sure that the deformation that I do here is very similar to its neighboring deformations. So anybody that I'm connected with in terms of an edge on my graph, I want to make sure that those deformations are as close as possible. And so the way they did that is they basically said, all right, what I'm going to do is I'm going to take the deformation that's here and basically apply it to another node. And If that other node moves to the correct spot that it is in, then great, we've got a deformation that matches. And so let's actually look at the math for that, because it explains better than what I just said. Regularization is equal to the sum over each one of the nodes. So this is the same as that. Notice how I drew it on top. I'm trying to do it that way. And then the sum of k is an element of the neighborhood of j. So we're going to go through each one of the connected nodes to the node that we're currently looking at, right? So this is just saying go through each one of the nodes, choose it as your main node, and then look at its neighbors. And then there's a weighting parameter, which they pretty much set to 1 in all their examples, but you can actually play with this. Then we have this. Rj G, let's make sure I get this right, K minus G I plus G, or I mean J, J plus T I, or J minus G, right, K plus G. Shoot, squared. All right. So what does this do? What does this do? Okay, so make sure I get the subscripts right. Yes. So this, remember, GJ is the that's the position of our node, right? And GK is the position of the other node, right? So we're basically subtracting them and basically creating a little vector from our current node to the other node, like that. Then we're using the rotation. We're applying the rotation to that guy, and we're rotating it a bit. And then we're also adding back the current node. So we're saying, hey, if I've got a vector to this guy, and then I rotate it, and then I add it back to this guy, because remember, this is just a vector. We basically are moving it to the origin. And we add it back to this location, and we translate it based on how much we're translating that node. That'll tell us the new location of that point. Well, actually, we really want that new location of that point to be the location of that point based on where it thinks it should be, which is the node with the point plus whatever translation it has. You don't have to worry about rotating it at this point, because rotating this node by the rotation of itself basically causes that node to just sit there and spin at the same point, so it doesn't actually move it in space. And so just all you have to do is add Tj or Tk to this to figure out where this node moves by its own volition, or the transformation associated with it. So you're saying take the transformation associated with J and take the point, which is a neighboring point, and apply that transformation to figure out where J would send that point. And then see if J or K's transformation will put it in the same spot, which makes perfect sense, right? You want this guy's transformation to be similar to this guy. It's never going to be perfect, right? Because there's going to be the sort of overall deformation of this mesh. But you want them to be as close as possible as it can be. Now, Joe pointed out a problem. Joe pointed out a problem. It's a very good problem. And that if you had a mesh, and the deformation graph, remember it's a graph, and they even have examples of this inside their paper, where the graph is just a single line of edges. And they're all collinear. Well, if I do this, remember what I'm doing. I'm taking this point and its rotation and translation and applying it to this. Well, if I do that, this rotation is basically pointing so that it's rotating around this point when all these guys are straight, right? So basically, if I want this rotation to move this point so that this point is where it is, there's an infinite number of rotations that'll get me that. I can basically spin this guy around this edge in any different angle, and it will get me to this point. The only time when this doesn't work is when there's a bit of an angle, right? If there's this, then because this rotation would then take me away from this, I'd actually, remember I'm taking this vector and I'm actually spinning it, I'd spin this then. But if this vector is pointing directly at that point and they're all in a straight line, any rotation at all will keep me at this point. That's kind of annoying. And is probably a bit of an issue. So if you actually took this and used it to deform hairs or something, and you pulled all your points so that they were all collinear, then this regularization thing is all of a sudden going to give you the exact same energy for an infinite number of rotations. They all have to be pointing along this way. Like, you can't rotate it like it so it comes out of the screen. But as long as you rotate in this direction or along any rotation, you're going to be good to go. This is an issue that the paper didn't talk about. It probably doesn't come up all that often, and maybe you could put some stuff in there to alleviate it. But it's something to think about. This could actually, if you were implementing this, this is the very first thing that the artists are going to do, because it's for artists. All right, so for the most part, this works great. And then 3, constraints. We want an energy called energy constraint equals, and this is 1, and write it over here. This time we use L equals 1 to P for the different number of constraints. And we basically want the location of where the V index sub L is deformed by the deformation graph according to the equation. So this is basically where the node on your deformation graph ends up, should be equal to Q sub L squared. And this is the user supplied position of constraint L. All right. So putting together all these 3 things, if you add up energy of rotation, energy of regularization, and energy of the constraints, you get a total energy of your system. And the system consists of rotations and translations at each one of the points on your deformation graph. And what we want to do is figure out values for each one of the rotations and values for each one of the translations that make these energies get as small as possible. And at this point, we stop and we think, ooh, I bet other people have done this. I bet other people have solved these kind of problems before. And in fact, the guy who invented gravity did this. And Newton did this, and Gauss did a huge amount of electromagnetic work. Evidently, one of the smartest people that ever lived on the planet was also working on this kind of stuff. And we're going to take a break from this thing and step aside and look at some of the mathematics behind this. And I know these equations look kind of scary, but think about what's actually going on. Actually, it's not all that crazy. Here we are, we're running sums over all the points, and this is a smaller list of points because not everything is constrained, but we're just running a sum over all this. So each time we go through and add this up. And then look at what's going on inside this. We're taking 2 values and dot producting them and then squaring them. And we're seeing squares all over the place. And in fact, this symbol, and in fact, this should have a 2 down here. This is the 2 norm, which takes the length of this vector that's being produced. Remember, this is the point where all this math tells us where this vertex should go, and this is where the user is telling us where to go. So this is a little vector. It's a little 3-element vector saying, how far off are you? Well, these double bars with the 2 on the bottom basically say, tell me the length of that vector. And the length of the vector, well, that's just x squared plus y squared plus z squared, right? It's just the elements of the vector, but we don't want the square root. The square root gives us nothing. And so they square this. So we put a square on that, and that basically gets rid of this. And all of a sudden, we've got x squared plus y squared plus z squared. Wait a sec, there's something squared plus something squared plus something squared. And in fact, if you look at this little section right here is kind of a V on its own. This is telling us where we would transform one of the neighboring points. And this is a kind of a cube, right? So this is doing the exact same thing. We're subtracting a vector, I mean a point location from another point location and getting a vector. And then it's embedded in these bars, which is doing the same thing. So when you look at this, and we sum up E rotate plus E reg plus E constraint, what we actually get is this great big sum over whatever of something minus something squared. Right? Whether it's this or this or this, or or quite frankly, it could be just something. In fact, let's get rid of this something and just replace that with an f. Where f is a function. In fact, we could even replace it with f of x, where f is a function on some value, whether it's the column vector or the vector, the difference between these 2 points, or the difference between these 2 points. That's the thing that we're actually doing. Oh. This is a least squares problem, and this is exactly where this comes from. We would like to make this number as small as possible, and it's basically a sum of things that have been squared. Now, literally, when you see the least squares problem, this is what you think about. Something is being squared to get rid of negative values, which would just throw us off. And we're trying to find the smallest value possible. Now, there are 2 kinds of these problems. Well, there's multiple, a whole bunch of these kinds of things, but we're caring about 2 different kinds. There's linear least squares problems, linear, and nonlinear.
It's actually also worth mentioning that the square is being added so that which is the premise for any optimization problem, that we make the problem a quadratic one, right. So that the solution starts looking like a parabola, which has a minimum, which is what we are trying to do for an optimization.
Oh yeah.
And the second and third term, the regularization and constraints, are completely linear in the sense that they could easily be derived to a form of ax minus b, which is a linear problem which we know how to solve. The rotation, though, has multiplications in the x vector, which we cannot represent using the x equal to b. So that's what's making it non-linear.
Abso-freaking-lutely. And just to graph out what Rashad just said, think about f of x without the square, especially in a linear kind of thing. F of x without the square, well, and let's not even draw it this way. Let's draw it here. F of x might actually look something like that, right? Where it's just a line. You put in an x, you get a value of x, f of x out. So this is x, and this is f of x. And this describes a linear relationship between x and f. Well, if you ask for the minimum of this, well, the minimum of that is, well, I don't know where the minimum of that is. But if you square it, all of a sudden some interesting things happen. And when it goes negative, not only does this sort of get reflected, but we're squaring it. So we get this nice little shape here that looks like that. Turns it into a parabola. And all of a sudden, figuring out the location of the lowest point is perfectly possible. Now, how would you do that? And by the way, this is a very simplified way of doing this. Remember, these problems, especially with linear kind of things, can produce curves that look like this. Even when you square them, it might look like that. And there you have local minimum and you have local maximum. You have all sorts of stuff that's going on. You can even have the worst of all things, or the most confusing of all things, a saddle point. And why is that? Well, if you remember from math, if I wanted to find the minimum or the maximum or anything of a function, one of the easiest ways of doing it is to look for where in this function, especially let's go back to this, for the derivative of the function, which is a little vector that tells you how this function is changing. The derivative goes down this way. How does this function change as I move an x? Well, eventually the derivative of this function is going to go to 0. It's not going to go up, it's not going to go down, it's going to go to 0, because at this point, the function is neither going up nor down, it's just 0. And at that point, we've got something interesting happening. And in fact, if you look at this, you can see where the flat parts of this curve are. You can see, and there's that. At each point where the derivative of this function goes to 0, you have either a maximum, a minimum, or a saddle point. And if you've got a simple curve like this, the derivative where it goes to 0 will tell you exactly where this thing is. So the nice thing about linear least squares problems is you end up typically with something that looks like that. Even if, and we're talking about not three-dimensional or one-dimensional functions, but think about even a 3D function. If I have a 3D function, f of x, and I've got x and y here, and I have a function f of x comma y, then I could have something that looks very parabola-like. It kind of looks, let's try to draw this, like a big bowl. Still, this works. If I can take the derivative of that function, when it goes to 0, I found a minimum. But the problem with this is you can't just take the derivative of the function with respect to x. You have to take the derivative of the function x comma y with respect to x. And you also have to take the derivative of the function x comma y with respect to y. And so the derivative of this function actually produces a vector. This is, now we're getting into sort of vector calculus, where at any point on this function, the vector tells you how this function is changing. And I probably actually should draw it this way. So if I'm at a point on this function, and I take the derivative with respect to x and y, it produces two values that tell me that this function is changing in that direction at this point. But still, I'm looking for this point on this function where everything goes to 0, where both the derivative with respect to x and the derivative with respect to y go to 0, the smallest point on this function. So now we're getting to the point where we can actually talk about this. Because remember, we're just talking about derivatives of functions. And we're going to get to this awesome trees on this. So we want to find, the whole goal of this is to find x, where x is a list of, a vector of things, which is equal to the argmin of x of f of x. And actually, they are very good about their notation in this paper. And f of x is a capital function that takes x in and produces a single value out. Single value. So that's a scalar function. It's not a vector function at this point. But this applies to vector things. And so a least squares problem says f of x is equal to the, and they put a 1/2 here to make the math a little bit, just so they don't have to write down a whole bunch of whatevers. F of I sub x squared. All right. So that is the definition. And look, that's the same thing I wrote down, except there's a 1/2 in here. And the 1/2 is there because we're going to take the derivative of this function. That moves the 2 down to there. You multiply it by 1/2, the 2 goes away. You don't have to write down 2's all over the place. The only reason that this 1/2 does not affect the results at all, because we want to find the smallest value. And the smallest value times 1/2 is still the smallest value. So you could have any number that you want there, and it would still be the smallest value of this function. All right, so that's our minimum value. And like I said, we could take the derivative of things like that. We could do this. We're going to jump ahead to how Newton solved this. All right, but first, before we go to Newton, we have to stop off at Taylor. Taylor series expansion is a way of looking at this function and sort of applying some calculus to it, right? We're going to say, you know what? Let's think about this. If I can evaluate f of x, each one of that's there, what would happen if I took x and added something to it? You know, added a little delta to x. So I changed it. Remember, x is a vector, so h is a vector as well. This is a list of numbers, and this is a list of numbers. And what we're going to do is basically add some numbers to each one of the numbers in x. And Taylor said, okay, well, wait, you know, actually, I can probably figure this out with calculus. We can first of all say, you know, we happen to know what f is at x. So let's start there. And then we can also do that derivative thing, right? We could actually say, let's compute the derivative of how f changes when x changes. And that's basically the slope, right? The derivative of this. And what we're going to do is take h and do a transpose on it. We're just using a little vector calculus here. And where we do g. We'll get to the definition of g in just a moment. And then we're going to do, and by the way, you can do this, the derivative, and then the second derivative, and the third derivative. And in fact, in the paper, they do that. They say, okay, well, this is the first derivative, and this is the second derivative. H, T, H, H. And these guys are all vectors. That's a matrix. That's a vector. And then plus O. And you'll always see this, and I thought I'd explain this in a moment. Whenever you look at Taylor series expansions, they basically start off with the value of the function at the current location, which you assume you can figure out. Then they start taking the derivative of this function. That's what g is. H is just this guy. And we're going to take the derivative of this function with respect to all those other all the elements in x, and multiply it by a value that we're changing. And then we're going to take the second derivative of that, and that's this thing. This is called the Hessian. And we're going to use that to say, okay, not only do we want to know how it's changing, but how the change is changing. And then we can do the third derivative, the fourth derivative, the fifth derivative. We can keep doing this forever. But sometimes they just eventually stop and they say, you know what? There's going to be some error left over, because this thing is supposed to equal. This thing and this thing are supposed to be the same thing. But eventually you're going to stop taking derivatives. And whatever you do is going to create a little bit of error. So we're just going to stick this in here, and we're not going to care about that. We're going to assume that as long as that error is okay, this will work for our purposes. So sometimes they'll stop right there. And in fact, we'll see that in examples here, and everything else is considered an error. But in this case, they've drawn it out to the second derivative, and so you get a little bit of error there. Now, let's look at G. We just saw G. G is equal to the derivative of x, which is equal to derivative of f of, with respect to x1 of x. And this is a big vector, right? Derivative of f with respect to x2 of x. You put that in there because the derivative can change based on location in space. All the way down to the derivative of f with respect to xn, however many numbers you've got here, of x. All right? And then think about h. H is just a change in x1. Let's do it this way. Change in x2 all the way down to change in xn. All right? So think about how this is going on. What we're going to do is turn this on the side. We're basically doing a dot product. We're dotting this with that. So we're taking the changes in x and multiplying it. So we're taking this guy and basically multiplying with that. This guy and multiplying with that, and so on, all the way down. And then we're adding that to our original thing. So this is saying, how much does f change if you change x? And you're saying, well, I'm going to multiply this by a small amount. And that will tell me how much f changes due to this change in x. Then we're going to add it to how much does f change if you change x2. And we'll multiply that by a small change to x2 and add that to the result. And eventually this is going to produce a change in f that we're going to add to the value of f that was produced at x. So really cool. We'll come to h when we get to h. Well, actually, let's really quickly talk about h. H is a big matrix. And it is the second derivative, well, partial derivative, x1 droop x1 squared. Okay? That's that. I'm going to leave off these x's if it's too much. Now this is this partial derivative of f with respect to x1, x2. This is partial derivative of f with respect to x1, xn. I'm doing this right? Yes. Rows versus columns. And then this is the partial derivative of f with respect to x1, x2, x part of x1. And this is partial derivative of x with respect to x2. Let's do it out x2. I could actually just leave out the square. And in fact, I think the square is inappropriate at this point. The only time you get the square there is when you do that. Stay with notation. And so on. And so you can see what's going on here is this is saying, well, that's the second derivative. And so this is basically saying, how does the change? So you basically want to multiply this by the change of the change. All right, so we get that. But this is the partial derivative of f with respect to x, a change in x1 and a change in x2. So think about this. Look what we're doing. Remember, h is just a whole bunch of changes of x. So we're going to multiply this all the way through by changes in x1, x2, and x3. And that's basically going to say, well, this thing tells us that this is going to change based on how x2 changes. Then you multiply it again, saying, hey, change in x1, x2, x3 on the other side. And that basically squares x1 and x2, or the change in x1 and x2. And so this is basically telling you how f changes when you square the change of the x. It's kind of cool. It combos everything. This is a little bit more complicated to create than this because there's a lot more differentiation in there, but it's still totally possible. And you can kind of imagine what the third derivative one would be. It would be bonkers. So we don't even want to go there. We're not going to go to third derivative. All right. So think about this. We have f of x, and we're looking at it to see how this changes if we add a little wiggle to x. We take the current value of f, then figure out how the f changes and multiply it by that little change, and then figure out how f changes again and again. I mean, the second derivative, the rate of change changes, and then multiply it by the changes squared, basically. Add all this up, and we get a really good approximation of our result. If we do that, we should get rid of the O because we're just saying, screw it. Okay, all right. We can believe it or not, we can probably do this. I'm going kind of slow. I've got 15 more minutes, but we can probably do this. So, are you ready? I want to find, let's see. Right. There's a necessary condition for a local minimum, and that is when f of x equals 0, right? The derivative of f of x is equal to 0. That's, again, our little parabola thing. When the slope goes to 0, we want this to be 0. Well, f of x is equal to g. Well, sort of. Let's put a g star there. This f of x is a scalar, and g star is a kind of a sort of, hey, this is kind of close to that. So what we want is to find out where this thing goes to a series of zeros. If we can find that, then we've got a minimum for this function, or maximum. And they talk about looking at this bad boy right there. This can tell you whether you get a minimum or maximum. I'm going to skip over that because for time. All right. So, just want to make sure we've got this. Newton said, all right, if we've got that, just want to make sure that we do this right. Right, so hold on just a minute. Okay. Just going really quickly. So we want this. All right, so here we go. Newton thought of this. He said, what we want to do is find a point where the derivative of this thing, is equal to 0, right? So he's saying, I want this guy to be equal to 0. And again, that's this whole thing, because I've taken the derivative of this guy itself. All right? So now he said, if that's the case, this is equal to the derivative of f of x. Just think about this. The derivative of f of x is not 0. We're at some point here on our little curve, and what we want to do is find the x plus h that gets us to this point. And so the derivative here is definitely not 0. It's going up or doing something. It's not the right value. There, it does go to 0. So we're going to take the derivative of this side, and we get plus f double prime x h plus, and we're going to leave off everything else. So basically, we've taken this and taken the derivative of that, and we've taken this and taken the derivative of that, right? So this is the derivative of f of x, which should give us this guy, and that's that. All right. So if we set this to 0, and we leave this thing off here, and we'll turn this equation into this, then we can do something interesting here. We can move this over here, right? And we can do Newton equal negative f of x. So think about what I just did there. I did a quickie. I want to find the location where this value, the derivative of this guy, goes to 0. So we took the derivative of this side and produced this. Well, if I set this to 0, I can take this and slide it over here, and I've also switched things over. So sliding it over to this side means multiplying it by -1 and adding it to both sides of the equations, and I get this, right? And then this, when you're looking at this equation, is actually the Hessian. This is that matrix that I've created at that point. So I'm going to leave this guy here. I'm going to say, whoa, wait, oh, check it out. I've got this thing. So this is G. All right. Is that right? Well, it's actually HG. That should be a vector. Right, and it is. This is G. This is totally G. I'm sorry. This is totally G because you're taking the derivative of this with respect to a vector value. So you're taking the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z, and all that kind of stuff. And this is the Hessian. This is the second derivative of this. So think about what we've got there. We've got a little matrix that is H. We've got our delta x, delta x1, delta x2, all the way down to delta xn equals the derivative of f with respect to x1, the derivative of f with respect to x2, and x2, all the way down. And then there's a negative sign right there. Ooh, wait a second. This is something we can actually compute. So if we can figure out this, which is a whole bunch of partial derivatives, we can figure out this, then this becomes an AX equals B kind of problem, right? And we've talked about AX equals B kind of problems inside the Chalk Talk for basically forever. In MATLAB, if you do X equals A divided by B, you will get the right result. Okay. And in fact, we aren't even going to talk about that. We're just basically going to say there are ways of solving this kind of problem. We're given this matrix and given this matrix, we can solve for X in there. Easiest way is to use MATLAB, but there's all sorts of different ways of doing it. And then that gives us an H, right? So to figure out the location of the minimum of this function, all we do is take X and add it to H. Now, you'd think that that would be enough. Well, if this was a linear problem, it would be enough. This will actually take you, wham, right to the bottom of our parabola. But if it's a nonlinear problem, where you've got some weirdness going on, or some nonlinear behavior going on, this will not work. What I'll often do is take you closer to the minimum that you're trying to shoot for. And notice, and this is a big problem, if I have an actual curve that's there and I start here, if that's my initial point, this procedure will find that location even though we're looking for that one. And there's nothing you can do about that. This is something that you've got to basically make sure that you're initializing your search for the solution in the right location. So once you've done this, this will find that. And whether we're looking for a maximum or a minimum, you can look at the Hessian in order to determine which way you're going. All right? So all of a sudden, and that's why I was talking about this being actually relatively easy, sort of. Think about what we started with. We have this function, which is just a whole bunch of squared things. We have energy rotation, energy regularization, energy constraint, which got erased, which is just a whole bunch of square things. So if we can list off each one of these square things as a big vector and take the derivative with respect to all the values that are possibly changing, we can use something like this to figure out x. And that's exactly what they do. They take this big list of sums and start creating a great big vector. So the first element is the thing that's getting squared. So this is C1 dot C2. Second element is the thing that's getting squared, C1 dot C3. And then we'll skip down to like this one. This element over here is C3 dot C3 minus 1. And you're looking at this and you're like, well, wait, is that a number or is that a function or is that, what is that? Well, at this point, it's actually a mathematical equation because we're going to be wanting to take the derivative of this. And so we also have a list of our x's, right? So our x's, these delta x's or the x's that are the thing that go into my function, what are those? Remember at each node we have a rotation matrix, and we'll call R1, R2, R3, R4, R5, this is kind of gross, but R6 all the way up to R9, and then T1, T2, and T3, and we have one of these for each node. We can start listing off each one of these guys, all the way down to R9, T1, T2, T3, and that's just one node. So we keep going with all the rest. Now you think about this. We need to take the derivative of this thing. That's kind of, well, that's our function squared. And so you need to go through here and take the derivative of this thing with respect to R1 and take the derivative of this thing with respect to R2. Now, like I said, this goes on for frickin' ever because we have a lot of nodes. But C1 and C2 for a single node only change when you're actually talking about the rotations associated with that node. So the rotations way down at the bottom associated with node number 17 that we don't even care have no impact on the value of that. So the derivative of this value with respect to the rotations on another node are 0. And we love zeros. So what this does is produce a very sparse matrices of derivatives. The only time that these things change is whether or not one of these guys is there. But you can sort of see that this is going to be complicated. Like this thing is the thing that's being squared. So you're going to actually have down here an R times G minus blah, blah, blah. There's a great big one of these sitting right there. And it will depend on some more rotations and more translations. But still, it's only going to change when one of the neighbors is involved in that. So again, it's still going to be a relatively sparse result. So all of a sudden, we're thinking, okay, cool, wait, this is kind of cool. Because we have one of these functions. We have this, we can take the derivative with respect to x. We can throw it into this, and bam, we can solve it with this kind of thing. And what this will do is give us a huge jump towards the solution. And you do this a couple of times. And the nice thing about Newton's method is that as long as you're starting in the right spot, it's guaranteed to collapse very rapidly. The problem with Newton's method is you have to completely recompute this guy every single round, everything, every single one of these iterations. It takes a long time to actually compute this stuff. So this is an expensive per iteration method, but it's very fast once you get it going at finding the minimums. Now,
Is
is
it always guaranteed to undershoot the minimum?
Well, yeah, really good point. Really good point. So when they say, I skipped over this. Excellent. When they say the new x, the x solution is equal to x plus h, they back off and they say, oh, wait a sec, maybe that's not the best thing. X plus h times alpha. And this alpha is basically a line search where you're going to go, and the most robust way of doing this is saying, I'm going to add a multiplication of h to x, because I know that going in the direction of h is a good thing. It's the best thing, right? But how far do I go in the direction of x? So this basically says, let's do a little bit of iterations. If I'm on a crazy curve and I'm here, how far can I go in this direction? So that's always going to be in a linear direction before I start screwing with my results. And so there are conservative ways of doing this or not conservative ways. And in fact, in a lot of cases, people say, you know, it's relatively decent. You might get an overshoot or so, but if you set this to 1, you get pretty darn good performance with Newtons, and you don't have to do any line searching. But you can just do sort of a halfway, or you can say, I'm going to jump to 1, but if I get a worse result, I'm going to back it off by half, and then, you know, you can do some binary searching in order to get this thing, the right result. So you made a really good observation. Especially with extremely nonlinear problems, just adding this to this is maybe not the best thing. This tells you the best way to go, but how far to go is something that you still might want to search for. And with that, we didn't get to Gauss-Newton. Gauss-Newton, by the way, is easier than this. Gauss-Newton actually goes back to our original thing where there's a slight change. This side of the equation stays the same. This side doesn't. It means you don't have to compute the Hessian on this side. You don't have to compute the second derivative. And that makes a big difference. So Gauss-Newton is a little less accurate than Newton. You don't compute this second derivative matrix. You actually compute a matrix, the matrix that I was talking about, and then multiply it by itself. And the results are easier to figure out, but not quite as robust. So I'll leave that to the reader because it took so long. Does this make any sense? The whole thing is, at the core, if you start reading these papers, you see equations that look like this. 1 minute and we'll be there. Well, you see equations like this all the time. And then all of a sudden you think, well, wait a sec. I can figure out the value of the function because I have the function. If I could just get the derivative, then I can do Gauss-Newton. If I can get the second derivative, I can just do straight on Newton. And all of a sudden I can solve these problems. They aren't that crazy. And this works for both linear and nonlinear problems. So at the end of all this, what do? You pin some points with the constraints, you move them, you solve this thing, which gives us a big vector that changes the rotations and the translations. And the rotations and the translations will make sure that this energy is minimum. They move similarly and they satisfy the constraints. And all of a sudden you can start bending this mesh, or the deformation graph, in a nice, clean way. And then you change the deformation graph onto the underlying mesh, you get bendy objects. And because this is relatively fast, it happens in real time. Oh, so exciting. And the best thing is, Rashad has implemented this. So just use his thing. All right, guys, see you in the new year.